Now let's come back to our discussion about geodesics. Remember, they're supposed to be generalization of lines to any Riemannian manifold. We say that there are two ways to think about it, two ways to characterize them. One way is to think of geodesics as curves with no acceleration. So we have defined geodesics using this characterization. In particular, we have defined the notion of the covariant derivative of any curve on the manifold, right? This could be defined using connection or using parallel transport. And then we say that a curve gamma is a geodesic on M if and only if the covariant derivative of its velocity vector field is 0. Now we want to look at another way to think about geodesics. This corresponds to another way of viewing lines in space. So we can think of a line segment from P to Q as the curve of shortest distance, right, of shortest length from P to Q. Does this motivate us to think of geodesics as some kind of length minimizing curves? The advantage of this viewpoint is that we can use the tools of variational calculus, because in calculus, minimum correspond to critical points of functions. So one way to explore this viewpoint is to view this line segment as a critical point of some arc length function. Maybe we look at some arc length function whose domain is some family of curves from P to Q. And then in that case, this line segment is going to be a minimum of this function. And if the function is smooth, we can then use tools of calculus to find this. Alright, so let's explore this viewpoint. But to start with, we'll need a notion of length. We'll need a notion of distance on the Riemannian manifold. Now you might say, don't we already have a metric on the Riemannian manifold? Well, be careful, this metric is not the metric in the usual sense of metric spaces. This is a Riemannian metric. So it does give us a notion of length, but only locally on tangent spaces. We do not yet have a notion of distance between 2 points on the Riemannian manifold. So that's what we're going to do now. We want to define this notion of distance, Riemannian distance, and our plan is as follows. We want to define the notion of arc length of any specific types of curves, and then given any 2 points P and Q, we would define the distance between P and Q to be the infimum of the arc length of curves connecting starting from P and ending at Q, but specific type of curves. The kind of curves that we want to look at are those that are piecewise regular. That means these are curves such that we can chop off its domain into finitely many parts, on each of which this curve should be regular, i.e. on each of those parts the curve is an immersion of the interval into M. Its derivative does not vanish, so that we have an immersion of this interval into M. An example of a curve that is not regular is, for example, the Cups curve. So the Cups curve is not going to be regular at the origin here. The velocity vector at the origin is just going to be 0. So this does not immerse into the manifold M. Thus the condition of a curve being regular helps us avoid cups and kings. For each such regular curve segment, we can define its arc length to be the usual using the usual arc length formula in calculus, and then for an admissible curve we can chop it into finitely many regular curves and then add up those arc lengths. So we also have the notion of arc length for admissible curve. Now given 2 point P and Q, we can look at all the admissible curves, right, starting from P and going through Q, and look at their arc length. Then we define the distance between P and Q to be the infimum of the arc length of such curve. This distance gives a metric on the Riemannian manifold, and it turns out that the metric topology, the topology induced by this metric, is actually going to be equivalent to the original manifold topology. Okay, so now that we had the notion of length, let's come back and show that length minimizing curves are actually geodesics.